Hello everyone, welcome to chapter 3 of set theory, and we have been looking at quite a lot of sets recently where we represented the set in maybe this form. Say that my set contains 1 alpha and a, so I represented within curly brackets that these are the elements of the set. I gave you the elements explicitly, so this is called giving the elements explicitly to you, and a was the name of we named the sets too. So this form of representation where I give you the elements, where I list the elements contained inside curly brackets, is called the set roster form, or I'll just write roster form. So the name is not that relevant now, but this form of representation exists where I list the elements. Today we'll look at one other form of representation which is very intuitive to us because we have learned something called mathematical reasoning, wherein we have stated how to express a lot of statements in English mathematically, and it will be a more rigorously defined way of expressing the sets, representing the sets. So set builder form. I'll write abstractly what it means and then I'll explain. So say my set B I am representing with in this manner. I still write down the curly brackets, but I say that the set of all x's such that x has property P. So this is very vague and very abstract now, but I'll just use a couple of symbols here. So such that I am replacing by this symbol, a colon symbol, but a colon becomes somewhat tedious to write down a lot of times. So in books you'll see this colon symbol. I'll often use this bar just to say such that I'll use this bar. So it should be read as such that, and x has property P. What does that mean? Well, to show what it means, I'll give you an example. So say that I have a set n, I'm calling it the script n, such that, so the set of all x's such that x is natural number. So now this is a statement which is well defined. So if x is a natural number, it will belong to my set. If it is not, it won't belong to my set. So I can just give you elements -5 say, and you can tell me whether it belongs to the set or not. And we know that 5 is not a natural number. 5 does not have the property of being a natural number, so we won't put that in our set. 0 is not a natural number, so 0 won't be in the set. 1 is a natural number, 1 will be in the set. So this way of representation is called the set builder form of representing a set. If we build the set according to the given description, it's also called descriptive form in a lot of places. So set descriptive form. So how to write the set builder form of the sets we are thinking of is a good exercise, and we'll do a lot of those problems now. I have here written down a couple of problems. So we'll looking at a lot of examples, we'll try to understand what it means. So this is my I'll call this example 1 for now. Let me give you another example of what I mean by set builder form. So this till now we don't know what it means. We've just seen one example. Let us look at more. I'll give the set as S for squares. So essentially I'm collecting all the squares of integers. And the statement I just said in English, I wrote it down in formal mathematical language. So the set of all x squares such that x is an integer. This is the symbol for integer, do you remember? Integer. So it comes from the word zol. So this is the symbol for integer. So whenever x is an integer, what do? I square it and I add it to my collection. So say that I've given you 3. So does it belong to the set? Well, is 3 a square of some integer? No. So 3 does not belong to S. And does 9 belong to S? Well, it does, because 9 is the square of 3. So what will our set actually look like? Here we knew what the set would look like, so I didn't write it down. But if you had to, it's good to always write it in the roster form. So I leave this to you. This is an exercise to you. But this set, what will it look like in the roster form? What I am asking essentially is, how do I state the elements? What are the elements in the set? Just list all the elements. So maybe I'll write the first element as 0, because 0 squared is 0. So then 1 squared is 1, 2 squared is 4, so 4 will be in my set, 3 squared is 9, and then I'll have 16, 25. So all the squares of integers are in my set. And negative 5 squared is also 25, negative 4 squared is also 16. So we need not repeat it. It's just a collection, so it's enough to mention it just once. So this is the roster form for the same set. So I have given the same variable name to S. These both mean the same things. So one way of representing is less tedious in a lot of places, so we'll use that way of representation. We'll look at these now. So I'll represent a new set now. Mu, so just to say that the name can be anything, mu is equal to the set of all x's such that x square plus 1 is equal to 0, and x belongs to R. X is a real number. So what will this set look like? What elements does it contain? So just after you have thought about it, you should come back. So just looking at this property and in conjunction with this property. So this comma here stands for the AND. So this is the symbol for AND. So comma stands for AND here. So x should obey both the properties. So x has to be a real number first of all, and x square plus 1 has to be equal to 0. So immediately what do we think of? We'll look at places where x square plus 1 is 0. So for what value of x's does this happen? So this would imply if x square plus 1 is 0, then x square should have been equal to minus 1, and the square of some real number has to be negative. So does this have any solution? Do we have any values for x that this happens? No, right? You should think about this. The answer is no. So for no value of x, for no real number x, does this happen? So this does not happen for x belongs to R. Hence, when this property is obeyed, this is not. Therefore, our set contains nothing. So our set contains nothing. It's a null set. And this can also be called the roster form for this set, because I have listed the elements and I have said that there are no elements that obey this property. So this turns out to be a null set. So maybe this way of representation here is more useful, right? You just give me a null set rather than giving you this property. So it depends on the scenario. Which example was I in? So this was a third example. I'll give you a fourth example now. Fourth example is x such that x is a prime number and x is a divisor of 6. So this is a set. I'll call this set K. K does not mean anything here. So what does this set look like? Well, first of all, you notice that the definition is more in English than in math, so it's not that rigorous, and it does not need to be inside builder form. So this is accepted unless the meaning is understood. It is accepted. So x has to be a prime number and x has to be a divisor of 6. So listing prime numbers is more difficult than listing divisors of 6, right? So we will first list the divisors of 6. 1 is a divisor of 6, 2 is a divisor of 6, that is a factor of 6. So 3 is a factor of 6 and 6 itself. So but x has to be prime also, because that's the second property. Hence our set K would contain just 2 and 3, because 1 and 6 are not prime numbers. So this is the roster form of the set, and this explains why that's the roster form. This explains the reason behind putting 2 and 3 in my set. So this is the set builder form, descriptive form. So now things are clearing up what we mean by descriptive form. So I'll give you we will do the exact opposite thing. I'll give you the roster form, and maybe you'll have to tell me what the descriptive form or set builder form is. So essentially you'll have to find a pattern and give me that pattern. So 1 by 2, 2 by 5, 3 by 10, 4 by 17. These problems are taken from your syllabus books, so you'll look at these in your class maybe. So this is my given set. Maybe I'll write 2 more. 6 by 37 and 7 by 50. So these do look random for now, but we'll have to spot some pattern and we'll have to describe each and every element in the set in some manner. So how do we go about this? And the numerators, I can see that they are natural numbers, right? So if x had belonged to natural numbers, then the numerators have been taken care of. So I can just say x by, or maybe I'll write n here, the set of all natural numbers n. So n by something. So n by what should it be? The first element is 2, second is 5, third is 10. Okay, so 2 is, so if I write n square plus 1, will it work? Because it's 1 more than the square of the numerator, right? Each number is. So 5 square is 25, this is 26, 7 square is 49, so this is 50. So does this work? I think so, yes. So how do we write this as a set? Now we know what the elements are, in what form the elements are listed. So how do we write this in set builder form? I'll call it A. So the set of all, I'll give a variable x such that x is of the form n by n squared plus 1 for n belongs to natural numbers, right? So that's the form. Does this work? So take one natural number here, you substitute it here, and you list the x then. So this is my set builder form now. Set builder form for this given set. This is in roster form. So this form was easier for this writing down this set, right? This is more intuitive, and I'd prefer this form over that one for this situation. One more example I've written down as maybe n such that n cube is odd. N cube is odd. So what will this set look like? So I just have this is my last example, I think, and I'll have one more after that. That will not be an example of a set, so that will be interesting. So okay, so this is my set. I'll call it what is the fifth? Is it the fifth example? No, this is the sixth one. So the set of all n's such that n cube is odd, and it is understood that n is a natural number. I'll write it down. It's always better to be specific. So n is a natural number and n cube is odd, and we'll collect all such n's. So we'll have to be a bit careful here. So say that if n cube is odd, so maybe take an odd cube, 27. So if n cube, that is this is 3 cube, if this is odd, then we'll collect 3 into our set. So 3 would belong to S. This would imply that 3 would belong to S. So what about 8? Is 8 odd? No. Then 2 cube is actually equal to 8. This would imply that 2 will not belong to the set. So do we understand what is happening now? So given any number, given any cube, we'll look at n and determine whether it's odd or even. So I think we can go one step further to write a roster form for this explanation. We can also look at when is n cube odd for any given n. So maybe you take an odd cube. So if n cube was equal to some odd number, maybe 2k plus 1, then what would have n been equal to? This is a bit difficult because n cube is equal to an odd number and you'll have to take cube root of both sides and simplify. So maybe you think of the other scenario. When is the cube of a number odd? So when is cube of a number odd? So what if the number is even? Can its cube be odd? So if the number is even, it will be some 2k1, that number, because it's a multiple of 2, right? So can its cube be odd? Well, no, because you can always factor out a 2 and it will be something, 2 times something. So if a number is not even, it has to be odd, right? So if 2k1, I'll call maybe 2 plus 1 is an odd number and I'm cubing that number, it will always result in some 2k2 squared and blah blah blah. So any a 2 can be factored out from this blah blah blah, and I'll still have a plus 1 out here, right? Plus 1 cube. So you should try to simplify this exactly. I've given you a rough simplification, so you should do this as your exercise. So just now what I've shown is, if a number is odd, if n is odd, this implies n cube is odd. And we have shown that if number is not odd, if n is not odd, this implies n cube is not odd. So we have shown that p implies q. We have also shown that not p implies not q, which would mean the same thing as q implies p. So we can say that p implies q as well as q implies p, and we can put an if and only if condition here. So if this red part was very confusing to you, I'd suggest you go and watch mathematical reasonings first, because everything that I just said here was discussed over there. So this type of reasoning is really important. It comes very handy throughout mathematics. So you should watch these videos and then come back for this red part. But if you have an intuition, just go ahead with it. So I have just proved that n cube is odd if and only if n is odd, or the other way around. So essentially what my set would contain, all this hard work was for saying that my set would essentially contain all the odd numbers, because n cube is odd, so n has to be odd. So my set contains these 1, 3, 5, 7, 9. So all these numbers are contained in S. So now you can verify whether n cube is odd, and it will be odd in all the cases. And you could also write the set. So this was the roster form of the set, roster form. You could also write this in set builder form, but a simplified set builder form of sorts. So I could also write this as the set of all odd numbers, the set of all 2k plus 1s, such that k belongs to n. So this is also a set builder form of the same set. We have given you two set builder forms. Set builder. One is a bit simpler than the other. So now for that last interesting example we had, remember in some lecture, I think lecture 2 or 3, I told you that I'll give a set which is well defined, which I will be defining properly, but yet that's not a set. That leads to a paradox of some sort. The name paradox might be new to you. Paradox essentially means there's no yes or no answer for that. Even if it's yes, it would lead to a contradiction. Even if it's no, it will lead to a contradiction. So that's a paradox. We'll look at paradox in higher studies in detail maybe, but for now that definition is kind of loose, but it might hold. So I am defining the set A, or I'll call it R because this R has a name to it. I'll tell you that later. So X, the set of all X is such that X does not belong to R. So that's why the problem is. Now you have to pause the video, you have to think about this because this is very interesting. Think about what elements belong to the set, and hoping you have spent a couple of minutes with it, and I'll tell you now. So if I have given you X and I am asking you to put it in the set if it does not belong to the set, so that's a contradictory statement. That's a paradoxical statement, right? Which means that if say that 2 belongs to R, then 2 has to have followed this property by the definition of the set. Because 2 belongs to R, it has to follow that property. But this property would imply 2 does not belong to R, and this would be a contradictory statement. These both being true together would contradict each other. So okay, so maybe 2 does not belong to, maybe we don't know about 2, so maybe to start off with, say that 3 does not belong to R, then it obeys this property, then it had to belong to, this implies that this had to belong to R, and this is again contradictory. So do you see the problem? If we say that an element is contained in the set, it's a problem. When element is not contained in the set, it's a problem. So this defies our naive set theory definition. Even though I have given you a rigorous definition of the set, a lot of problem happens. So naive set theory fails here, and this part is this example part is not in your scope, but I just wanted to tell you that there are places where naive set theory does not hold. That's why it's called naive. It doesn't know anything, it's inexperienced. So these problems were later resolved by something called the axiomatic set theory, and this was suggested by someone called Bertrand Russell. He was a very famous British mathematician. I don't know whether I am spelling him correctly or not. So Bertrand Russell gave this paradox. That's why this paradox is also called Russell's paradox, and this defies the naive set theory definition. So I hope you found that interesting, and we have just seen how to represent set builder form in set roster form and vice versa. So I hope you had fun. Thank you.